So good morning students, welcome back to online chemistry classes. In the last lecture 13 we have completed almost all regarding hybridization, VSCPR theory. Okay, when I told you regarding resonance, how to write the resonance structures, what is resonance energy, what are resonance structures, okay, and what is resonance hybrid. Especially I have given you resonance structure of carbonate radical, sulfide radical, okay, nitrate radical, even sulfate, SO3 molecule also, even taking benzene examples, more than enough. But this will help you in writing the resonance structure. Resonance I told you already, it is nothing but delocalization of pi electrons or shifting of pi electrons or sigma electrons from one position to another position. Why? So as to become stable. Okay, right. Now without wasting the time, now we will last part of this chemical bonding, that is molecular orbital theory. See, why there is a need of MOT? Generally question arises because you have studied Lewis dot structure, Lewis-Langmuir theory, that's only, then valence bond theory, then one hybridization and VSCPR theory, valence and electron pairing constant theory. Why there is a need? See, there is a need of molecular orbital theory because there are demerits of VBT, valence bond theory. See, first you should know this. What are the demerits? Demerits of VBT, valence bond theory, or disadvantages of valence bond theory. See, valence bond theory cannot explain. It cannot explain the paramagnetic nature. The paramagnetic nature of O2, that is dioxide. That's the main drawback. Next drawback, it cannot explain. Cannot explain molecular spectrum. Molecular spectrum. Okay, formation of molecular spectrum, and it cannot explain. It cannot explain not only molecular spectrum. It cannot explain existence of H2 plus, He plus, O2 plus, O2 minus, O2 minus, that means ions. And also it cannot explain the arrangement of electrons. Arrangement of electrons in electron deficient compounds. Electron deficient species like VF3, ACL3, sorry, ALCL3, APCL3, AS42, AS42, which are generally called as Lewis acids. Okay, then it cannot explain nature of coordinate bonding. Coordinate bonding. So these are the limitations of VBT. That means valence bond theory can explain formation of covalent bond through orbital overlap picture and also the geometrical shape of the polyatomic molecules, but cannot explain a species like electron deficient species and existence of ions. This was not explained. Okay, right. So these are the demerits of VBT. To overcome this, there is a need of another theory called as molecular orbital theory, which was given by F.H. Hood and R.S. Silicon in the year 1930, and in the year 1932 it was modified by Slater and Pauling once again. Right? Okay. So let us understand what are the salient features of molecular orbital theory. What are the salient features of molecular orbital theory? See, these are the d variants. See, what are the d variants? Cannot explain the magnetic property, not only oxygen, all magnetic property, formation of molecular spectra. It can explain only atomic spectra but not molecular spectra, existence of the ions, positive or negative, and arrangement of electrons in electron deficient species, and even the nature of coordinate bonding. Okay, right. Now, to overcome these limitations of the VBT, valence bond theory, next molecular orbital theory was put forward. It was given by, see, it was proposed by F.H. Hood and R.S. Silicon. F.H. Hood and R.S. Silicon. R.S. Silicon in 1930. In 1930, to explain the formation of covalent bond. To explain the formation of, once again, covalent bond. But the existence of especially ions, and to explain the magnetic property and calculate bond order. Okay. And this was later verified by Slater and Pauling in the year 1930. Then what are the salient features? Salient features of molecular orbital theory. What are the salient features of the molecular orbital theory? Number one. Students, you already know what is atomic orbital in atomic structure. That was explained by me. What is atomic orbital? It is a 3 dimension is in the space where there is a probability of finding electron maximum around the nucleus. But here you are going to study molecular orbital. How molecular orbitals are formed? Molecular orbitals are formed by combination of 2 or more atomic orbitals. Prior that of nearly same energy and proper symmetry. That is important. Okay, that's what these molecular orbital theory. The reason around the nucleus of all atom, where there is a probability of finding electron is maximum, is called or are called molecular orbitals. That means first he has tried to give you definition. What are molecular orbitals? They are the reason around the nuclei, because they are formed by 2 atoms. Every atom has different nucleus. Therefore, the reason around the nucleus of all the atoms where there is a probability of finding electron is maximum. I will repeat. The reason around the nuclei of all the atoms where there is a probability of finding electron is maximum is called molecular orbitals. And when the molecular orbitals are formed, they lose their identity. Means atomic orbitals lose their identity. And these molecular orbitals, new molecular orbitals formed, they are polycentric, not monocentric. That means the nucleus is not restricted to only one atom. It is restricted to all other atoms, or its electron density is distributed all over the atom, which can take part in formation of molecular orbital. So that is the meaning of what? Polycentric. But what is the first salient feature, students? The reason around the nuclei of all the atoms where there is maximum probability of finding electron. Maximum probability of finding electron are called molecular orbitals. Okay. Right. Now, secondly, that means in the first point they are trying to give you the definition. Okay, that is molecular orbital. What is atomic orbital? It is also the region around the nucleus of atom, only single nucleus, where there is a probability of finding electron around the nucleus. But if it is between the two nuclei, around the nuclei, then it is called molecular orbital, because molecular orbital is formed by a combination of two or more atomic orbital along the internuclear axis or sideways. If it is along internuclear axis, once again sigma bond. If it is the sideways, it is pi bond. Same concept, no change. Okay. So molecular orbitals are polycentric. When molecular orbitals are formed by combination of two atomic orbitals of nearly same energy and proper symmetry. They lose their identity. And molecular orbitals are polycentric. Molecular orbitals are polycentric. They are not monocentric, they are polycentric. Polycentric means the nucleus of the atom is not only confined to itself only, it is also distributed all over the molecule, which can take part in formation of molecular orbital. That's why it is called polycentric. Polycentric, don't confuse it as many nucleus. No, that nucleus is distributed all over the molecule, which can take part in formation of molecular orbital. That is the meaning. Okay. This is the first two select picture. First definition of molecular orbital, then how molecular orbitals are formed. Okay. Nearly same energy, proper symmetry, very important. Same energy, equivalent energy, and proper symmetry. Improper symmetry, see, orbital overlap not possible. Remember. Okay. Right. Then after this, now third postulate of this user, what is the third postulate? After first two, that is select features. Now we can switch on to the third one. What is that third one? Third one is, and just right here, one by one. Third, that is select feature. Molecular orbitals. Molecular orbitals, okay, are described by wave functions. That is psi. The electron probability density. Is given by square of wave function, psi square. Okay, square of wave function, that is a psi square. This is how here just show. Psi give you the wave function, but the electron probability density is given by square of the wave function. Right? Okay. Then and how these molecular orbitals, another important character, just not to do, only those atomic orbitals and proper symmetry. Proper symmetry. Okay, proper symmetry can form molecular orbitals. Hence, number of atomic orbitals, number of molecular orbitals. Okay, number of molecular orbitals is equal to number of atomic orbitals. Number of atomic orbitals hybridize or undergoing combination. This is the fourth one. That means molecular orbitals are described by approximation method. It is called psi wave function in the form of upward displacement, downward displacement. But the electron probability density is given by the square of the wave function. Okay, and remember, only those atomic orbitals will form molecular orbitals only if they are having equivalent energy and proper symmetry. Otherwise, no, phase out. If they are of proper energy and proper symmetry, phase in. Improper symmetry, phase out. Once again, I will explain you here shape of the molecular orbitals. Okay, this is about fourth one. Then fifth one. Fifth postulate or second feature of this model. What is that? Now, when molecular orbitals are formed by linear combination. Okay, that is linear combination of atomic orbitals. It leads to bonding molecular orbital, and antibonding molecular orbitals. Antibonding molecular orbital. That means when these atomic orbitals of equivalent energy and proper symmetry, when they combine along the intermolecular axis, they form sigma molecular orbitals. Along the sideway, they form pi molecular orbitals. Here also same thing. But here you are observing one concept called as bonding molecular orbitals and antibonding molecular orbitals. BMO and ABMO. What are these? I will tell you, explain later. Differences. Okay, this is the fifth one. Then sixth second feature of this molecular orbital theory. Now, bonding molecular orbitals. Bonding molecular orbitals. Okay, they are BMO are stable with less energy. Antibonding molecular orbitals. Antibonding molecular orbitals, that is ABMO, are unstable with higher with more energy. That means antibonding molecular orbitals are having higher energy, whereas whereas molecular bonding molecular orbitals are having lower energy. Lower the energy, higher the stability. Higher the energy, lower the stability. Like this. And lastly, seventh one. Bonding molecular orbitals and antibonding molecular orbitals are designated as sigma, pi, delta, sigma star, pi star, and delta. Okay. And accordingly, lastly, molecular orbitals are filled according to outflow principle, Pauli's principle, what is Pauli's exclusion principle, and okay, these are the 8 select features of molecular orbital theory, right? So first one, see, molecular orbitals, no doubt they are formed by a combination of 2 atomic orbitals, but the probability of finding electron where, that means the region around the nucleus of nuclei of all the atoms where there is a maximum probability of finding electron are called molecular orbitals, right? And these molecular orbitals, when they are formed by a linear combination, they lose their identity and they are polycentric. And generally, these molecular orbitals are described by psi, that is wave function psi, and their electron probability density is given by psi square, square of the psi square. Okay. Right, and when molecular orbital, that means this number of molecular orbitals is equal to number of atomic orbitals undergoing combination or hybridize. But remember, the condition is only those atomic orbitals will form these molecular orbitals with proper symmetry and equivalent energy. Otherwise, they won't form the molecular orbitals. Here also, they undergo by sigma overlapping, pi overlapping. Sigma means along the internuclear axis and pi means along the side waves. Okay, but they are represented like this here. Remember, they are represented, designated as I told you, sigma, pi, delta, sigma star, pi star, delta star. Bonding and debonding. That means that they are formed by linear combination, by approximation of the wave function that leads to PMO formed by addition overlap, APMO formed by subtraction overlap. Further, I will tell you the differences. I will explain you in detail what is this linear combination of atomic orbital principle, students. Okay. So this is about select features of molecular orbital theory. And remember how these molecular orbitals are filled. These molecular orbitals are also filled as usual. How atomic orbitals are filled according to 3 rules: Aufbau principle, Pauli's principle, and Hund's rule. What is Aufbau principle? Electrons enter into various molecular orbitals according to their increasing energy levels. And also, no 2 electrons can have values of all the quantum numbers same, because orbital accommodate, molecular orbital here also can accommodate only 2 electrons, and these electrons cannot have values of all the quantum numbers same. And they pair up singly. That means first they occupy singly, then pairing starts. Here also, that means molecular orbitals having same energy are also called degenerate molecular orbitals. In degenerate molecular orbitals, electrons start pairing unless and until all the orbitals are singly occupied. So this is all about select features of molecular orbital theory. This can also be asked for one big question for 4 marks. Right, select features means all these have to write. 8 points for 4 marks. Each carries half of marks. Okay. Right. Now with this background, I will take you to next. What is this linear combination of atomic orbitals? LCAO method or LCAO combination. Okay. Right. We'll go step by step. Okay students, now what I am telling you, LCAO method, linear combination of atomic molecules. LCAO method. See, molecular orbitals, how they are formed? By combination of atomic orbitals. How? Linearly along the internuclear axis or along the sideways. If they undergo linearly along the internuclear axis, they form sigma molecular orbitals. If they undergo sideways, then they are definitely they form pi molecular orbitals. Let us see. What is this LCAO method? See, what is this? The approximation method of determining the approximation method of determining the molecular orbitals. Approximate method of determining the electron probability density, or else they can also tell as approximation method of determining this probability is just nothing but the process of determining wave functions of molecular orbitals. Okay, sorry. The approximation method of determining the wave functions. Wave functions of molecular orbitals. Wave functions of molecular orbitals. Wave functions of molecular orbitals is called LCAO method. Okay. That means by LCAO method, two atomic orbitals of nearly proper symmetry and equivalent energy, they undergo subtraction overlap and addition overlap. They undergo addition of the wave functions. Addition of the wave function. It is called bonding molecular orbital. They undergo subtraction overlap. They are called antibonding molecular orbitals. That's why we come here two concepts. What is first this B and O? Bonding molecular orbital. First I will tell you in detail with the diagram. B and O. Bonding molecular orbitals. Bonding molecular orbitals. Students. Okay, which is just in short form PMO. The molecular orbitals, definition. The molecular orbitals, definition is the molecular orbitals which are formed by addition overlap. Addition overlap of two atomic orbitals. Okay, is called or are called bonding molecular orbitals. Are called bonding molecular orbitals. Right? This is the definition. Now see here, as they are described by wave function, that I am telling you here. Wave function, especially it travels like a wave and is particle in nature. That's what I will show you. Suppose if you take two atoms, psi A, psi B, the wave function of the first one can be shown like this. Plus 1. This is, let us take it as psi A. Plus another one. Plus minus. Okay. This is psi B. A atom, B atom. Their wave function denoted by this. See, plus and plus only, minus and minus, they will overlap. This is called proper symmetry. and equivalent energy. They will say what will happen here? There is a force of attraction between the nuclei, and resultant is increases, and it also increases plus minus. This is called BMO, bonding molecular orbital. This is a psi BMO is nothing but psi A plus psi B. So electron probability density increases. Electron probability density increases. This is wave function. That means, see here, what is the wave function? Psi BMO is equal to psi A plus psi B, because we are formed by addition overlap, of atomic orbitals, wave functions. Okay, but the wave function psi square BMO is nothing but psi A plus psi B whole square. Got it? And this is A square plus B square plus 2AB formula. Psi square A plus psi square B plus 2AB means 2 psi A into psi B. That means here, see, the electron probability density increases by factor 2 psi A psi B. That's why electron density, see, there increases, and there is a force of attraction between the nuclei. This will become one. Right? This is the bonding molecular orbitals, and these bonding molecular orbitals, remember students, they are having less energy and more stability. They may or may not have node. But antibonding molecular orbitals compulsory node. That's the main difference between BMO and ABMO. Bonding molecular orbitals, they are having less energy, more stability, but antibonding more energy, less stability. There is a force of attraction between the nuclei here. Nuclei are wave functions of the atomic orbitals in BMO, but there is a force of repulsion in antibonding molecular orbitals. Okay, these are the main differences. This is how just what I have given you regarding information regarding bonding molecular orbitals. Right, students? Okay. Then, what are antibonding molecular orbitals? Antibonding molecular orbitals. Just let me add antibonding. Antibonding molecular orbitals. ABMO. See, the molecular orbitals which are formed by not addition, now this time subtraction overlap of wave functions of subtraction overlap two atomic orbitals are called ABMO, antibonding molecular orbitals. And here also, the antibonding molecular orbitals are given as psi star ABMO, and that is psi A minus psi B, because subtraction wave function. This is also psi square A minus psi square B, psi square A plus psi square B, just it is minus 2 psi A psi B. That means here electron probability density decreases by factor 2 psi A psi B, because here there is impulsion, not attraction between the nuclei. Got it? Very simple. Like this here also same thing. Now for antibonding molecular orbitals, okay, lobes plus minus plus. Lobes sign should also be opposite. For bonding, signs of the lobe should be same. For antibonding, signs of the lobe should be different. This is also very important. This is called proper orientation. Okay. Now see here, resultant now you will see. Result instead of increasing, they both are having same now density. But see, this is how for antibonding, electron density becomes minus. This is psi star ABMO, that is psi A minus psi B. Got it? So this is how we can explain antibonding molecular orbitals. Antibonding molecular orbitals are the orbitals which are formed by subtraction overlap of two wave functions or two atomic orbitals that are called antibonding molecular orbitals. And in antibonding molecular orbitals, there is a force of repulsion between nuclei. therefore they will what? They will not become homogeneous, they will split and they will divide. That's why they have compulsory, they have a node, but bonding molecule do not have. See, the wave function of the antibonding is psi star ABM. Star or asterisk is the indication of antibonding. Psi A minus psi B. Once again, electron probability density square. Psi A minus psi B whole square. Psi square A plus psi square B minus 2 psi A psi B. That means electron probability density decreases by factor 2 psi A psi B. See, decrease. Okay, that's it. So that's about antibonding molecular orbitals, and this is called as what? LCAO method. Here that means they form by addition overlap bonding, and subtraction overlap antibonding. But if they overlap this fashion along internuclear axis, they are sigma molecular orbitals. Alongside this, they are called pi molecular orbitals. Remember, students. Here also same thing. So that's about LCAO method. Okay, that is linear combination of atomic orbital principles. Okay. Now, what are the differences between these bonding molecular orbitals and anti-bonding molecular orbitals after understanding LCAO method, linear combination of atomic orbital principle, students? See here. Differences between BMO bonding molecular orbitals and ABMO anti-bonding molecular orbitals. That's our form. Right. One side I will write BMO bonding molecular orbitals, other side I will write ABMO anti-bonding molecular orbitals. Right? Okay. See, first one, definition. What is the definition? Molecular orbitals. Molecular orbitals. Right, formed by addition overlap of atomic orbitals or wave function. दोनों चले atomic orbitals. This is molecular orbitals. Right, formed by subtraction overlap of atomic orbitals, right? Okay, wave function is given by psi BMO is equal to psi A plus psi wave function. Regarding wave function, representation of wave function, here psi star ABMO psi A minus psi electron probability density. See here. Electron probability density increases by 2 psi A psi. That means psi square BMO is equal to psi square A plus psi square B plus 2 psi A psi. Here electron probability density decreases by 2 psi A psi. Means psi star ABMO is equal to psi square E, okay, plus psi square B minus 2 psi A into psi. Okay, very important, three important differences. Next, there is force of attraction between nuclei. Between nuclei in BM bonding molecular orbitals. Here there is force of repulsion. Force of repulsion between nuclei. Between nuclei in ABM. Right? Hence, it favors bond formation. It favors bond formation. Bonding molecular orbitals are having less energy and more stability. More stability. But here they do not form. Do not favor bond formation. Right? They do not favor bond formation. And remember, antibody molecular orbitals are having more energy and less energy. More energy and less stability. Remember. Okay? These are very, very important difference between bonding and antibonding molecular orbital. This can also be asked sometimes for 3 months. The first definition, wave function, electron probability density, and attraction and repulsion of nuclei, favor bond formation, and regarding energy and stability. Right? And always I used to tell you, this bonding molecular orbitals may or may not have nodal plane or node, but antibonding molecular orbitals always they have a nodal plane. This is another difference you can show, or you can write between bonding and antibonding molecular orbitals. Right? So these are the very important differences. I will repeat lastly. Bonding molecular orbitals may or may not have node or nodal plane, but antibonding compulsory they have a node or nodal plane. Okay? And bonding molecular orbitals they are just as shown here. Bonding and antibonding they are just differentiated by bonding without star and asterisk is given by antibonding molecular orbitals. This is how, say today I explained you what are the demerits of BBT and why there is a need of molecular orbital theory. Molecular orbital theory. Then I explained you in detail linear combination of atomic orbital principle. How BMO increases electron probability density. How and ABMO decreases electron probability density. And these are the differences between bonding and antibonding molecular orbitals. Okay, students. So after this, now we will study very importantly shapes of molecular orbitals. What are the different molecular orbitals? Then I will show you rules and regulations. Rules and that means rules for filling up of molecular orbitals and condition for overlapping of atomic orbitals to form molecular orbitals. That only in terms of shapes I will tell you, which will help you very easily in the tomorrow's class. But shapes I will show you today only within 5 minutes, which are not for your theory syllabus, purely for understanding purpose and for NEET purpose. Okay, NEET and Karnataka CET. Let us see. Because they are not given properly in the NCERT textbook, this has been omitted, that means they have deleted. Just that I will want to show you shapes of molecular orbitals. See how you an atomic orbital 1 is 3 yes. Here now molecular orbitals are only sigma, pi and delta, not more than that. That's why I am telling you. Let us see. Molecular orbitals. Shapes of molecular orbitals are molecular orbital. BMO and BMO. See See, available molecular orbitals are sigma 1s, sigma star 1s, bonding sigma 2s, sigma star 2s, bonding compulsory. And then we will have sigma 2pz, sigma star 2pz. Remember, pz orbital can form only sigma, not pi. And this side, pi 2ps bonding, pi 2p, pi star 2ps, pi star 2p. Remember, this is star. Bonding antibonding. So why are adding equal sign? Because they are having same energy. I am repeating. These are the various molecular orbitals. Sigma molecular orbitals, pi molecular orbitals. How you write atomic electronic configuration 1s, 2s, 2p, 3s, 3p, not like that. Here, these are the only available orbitals. Sigma 1s to sigma star 2pz last. They are only arranged like this. Just tell you sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Okay, then pi 2px, pi 2p, pi star 2px, pi star 2p. Okay, pi star 2p. Then sigma 2pz and sigma star 2pz. Right, these are the various available molecular orbitals, sigma and pi. Sigma they are formed by along the internuclear axis, and pi these are formed by along the side planes, that you already know. Remember, asterisk sign anti-bonding, without asterisk sign that is bonding. This is the differentiation you have to identify. Bonding, anti-bonding, bonding, anti-bonding, bonding, anti-bonding, bonding, anti-bonding. Equal sign by degenerate orbitals. Orbitals having same energy. Orbitals having same energy. Then only you can write equal sign. Otherwise, no. Please remember. Okay? Right. With this diagram, now I will show you how one is atomic orbital combined to form bonding and anti-bonding. If you know this shape of this will be same particles. Then this is different. If you know the shape of this will be same. Okay? Just 5 minutes I will show you phase in, phase out, which is very, very important, proper orientation in molecular orbitals. See here. This is 1s atomic orbital, 1s atomic orbital, atomic orbital. Okay. Now see, overlap along internuclear axis. Right, and will form sigma like this. This is sigma 1s d bonding molecular orbital. If it is 2s also same. See, there is a force of attraction between nuclei. That's only positive or negative. Got it? Okay. This is bonding. Like this antibonding. Antibonding subtraction overlap. 1s, 1s. Subtraction overlap means this will split. Okay? This will be like this. 1, another 1. Okay, this is antibonding. Psi star 1s. This is antibonding molecular. Shape of antibonding molecular. Remember. Got it? Bonding, antibonding. See, there is a force of attraction between nuclei. Homogeneous. This splits repulsion. That's why they will split. Favors bond formation, does not favor bond formation. And this is called nodal plane. Okay? Node. Remember. Okay? And this is the same for sigma 2s and sigma star 2s. Because s orbitals are split. Got it? Now, coming to next, sigma 2pz and sigma star 2pz. First, we will complete the sigma molecular orbitals. Sigma 2pz, see, pz, sigma 2pz, pz. See, minus, plus, minus. Here, lobes should be same. Otherwise, improper orientation. See, this will give right to plus plus minus plus. Nowadays, redundancy will be like this. Plus what full? एक छोटा एक बड़ा. This is sigma 2 b m o. Okay. So this will get, that is attraction. This is also will. Okay. This is called what we do Kaikarsan. Okay. For generally and joking sigma 2 b. Like this for antibonding, antibonding also same thing. Plus minus. But the thing is minus plus same. Those different sign. Okay, they overlap along the internuclear axis, and I told you plus minus plus minus. This will give rise to C. Now very interestingly, okay, plus that is minus plus, and then this is like this. They will split. This is called master to be head partner. A, B, and O. Antibonding molecular orbitals. Phase in, phase out. Favors bond formation, does not favor bond formation. This is called once again called node or nodal plane also. That's why I told you bonding molecular orbitals may or may not have node, but antibonding compulsory and node. And this is also 2pz, 2pz. Sigma molecular orbitals over. What is the remaining lastly? 5 molecular orbitals. 5 molecular orbitals only one see here. They lie first perpendicular to each other. 2px or 2py. Anyone. I will just take 2py, 2py. Will be same. Plus, plus, minus, minus. Gives rise to C. Plus, plus, minus, minus. Gives rise to 1C. Go like this. Plus another one minus. Okay, 5. So this is 2 pi 2py b bonding molecular one. Here there is a node. Remember, this is called node. Okay, then for antibonding, plus minus plus opposite. You will overlap like this, right? Plus minus plus, and this will give rise to C. 1, 2, 3, 4. Will all split. Plus minus just here, minus plus. But here we have 2 nodal planes. That's why I told you 2py will be same as 2px, 2pz will form sigma bond formation. Like this, these are phase in, phase in. This is called phase out. Antibonding phase out and bonding always a phase in. That means today I have covered very importantly. So these are helpful for you further in understanding rules for filling up of molecular orbitals. Okay, just I will stop here today. That means I covered today molecular orbital theory, select features, then limitations of VVT, select features of mod, difference between bonding and antibonding, LCO method, and very importantly shapes of molecular orbitals, sigma and pi molecular orbitals. Okay, stop here. Have a nice day. Enjoy. Thank you.
What is this?